Hi, I'm Ralph Bloch, the creator of the G-String program. In this presentation, I will show you how G-String handles missing data and how you can use the replications ability for special assessments when the number of repeated assessments can vary from one person to another. Have you ever tried to do a jigsaw puzzle and suddenly found that pieces were missing, so you couldn't complete the picture? That is surely frustrating. But hopefully you still have some other puzzles to spend your time with. The same thing can happen when you're trying to analyze your data. There are many reasons for missing data points. There may be transcription errors, or students may not know what to answer. They may not have enough time to complete the questionnaire. They may leave the exam prematurely, and many more. But that can have much more serious consequences when you try to do your processing using just Ur-Geneva. Robert Brennan, the creator of Ur-Geneva, was well aware of this problem. Page 13 of the Ur-Geneva manual, which you find among the various help options, explains how to proceed. Namely, you have to create an additional facet R that allows you to specify the sample size for each group of data points or even individual ones. So you can then even specify a sample size of 0 for one data point or others. That may work for small studies, but it is very cumbersome for larger ones. Here again, we have a fictitious 30-item true-false multiple choice exam for 123 persons to be completed. The authors expected a perfectly completed data set just like this, which would have resulted in a wonderfully significant test result where 86% of the subjects' total score variance could be explained entirely on the basis of subjects' variance, while only 14% would have to be explained by test idiosyncrasies. But instead, they received this data set full of holes with 550 out of a possible 3,690 scores missing. The corresponding analysis results were somewhat less satisfying. Just a minute! Shouldn't Ur-Geneva have outrightly rejected this dataset full of holes? G-String is using a trick. Remember that generalizability analysis is based on a linear model of statistics. It is not interested the least in the value of the score itself, but only in the variances of the facet effects. So we can easily perform a linear transformation by subtracting the mean gross score from each individual score and replace the missing values with 0. By stepwise and randomly deleting individual scores, we can then follow how raising the percentage of missing scores affects the analysis results. These are plots of the generalizability coefficient and the index of dependability against the percentage of missing scores. Both decline steadily but slowly as the percentage of missing scores grows. Similarly, universe score variance, absolute error variance, and relative error variance vary too, but somewhat differently with growing missing score percentages. And the same holds true for the variances of the different facets and their interaction. As long as the percentage of missing scores is small enough, we can use this automatic method to judge whether the test results are generalizable or not. Obviously, we have to use judgment about how to handle the scores of candidates with incomplete results. But as long as the E-rho square is less than 80%, we can still use the results for high-stake exams, since the corresponding results for a complete dataset are likely to be higher. Only a fool would make a far-reaching decision based on a single toss of a dice. Maybe if Caesar had tossed that dice a few more times, he wouldn't have crossed the Rubicon and history would have taken a different course. Yes, replications matter. Replications are the daily bread of every researcher. We replicate while keeping conditions constant to test for stability of results, and we vary conditions to discover dependencies. And sometimes the number of replications is part of the protocol, and sometimes we let the course of events dictate the number of required replications. A typical situation for replications in generalizability analysis is an assessment where different persons are assessed repeatedly, but not all the same number of times. Let's consider clinical clerks in medical school who are going through various compulsory and elective rotations. In the planning stage, the number of replications per student are not yet known. The end-of-year score record actually contains the number of occasions a particular student was evaluated. T-string can count these and pass them on as a sample size for facet O occasions. This occasion sample size frequency is then automatically inserted in the control file for each student, and if we were limited to Urgenova alone, we would be forced to laboriously prepare the control file by hand, counting the scores for each student. Typically, this kind of analysis results in lower overall coefficients of generalizability, since individual items, such as cognitive and behavioral performances, tend to be less well correlated than performances of an identical type. Also, the heterogeneity of raters is not averaged but ascribed to each individual evaluation, that is, each student. G-string has Urgenova at its core, a machine language program designed by Robert L. Brennan, who is rightfully considered the guru of generalizability analysis. Urgenova can basically handle any problem involving both balanced and unbalanced designs. But some designs require the manual preparation of complex control files and provide relatively little user guidance. G-string relieves the user of much of this burden. But it is left to you, the user community, to engage in order to maintain and keep this tool azure by visiting and using the appropriate GitHub repository. Thank you.